We're going to do some practice now. We're going to practice graphing a rational function, and we're going to do that in our problem journal. And before I get started on that, I just want to remind you that you have this document, or you should. It's I usually print these out in blue for the class. This is a reference document. I call it a frame. And this particular frame is about graphing rational functions. And if you are attempting to graph a rational function to practice, and you're not exactly sure how to get started, or you think you're missing something, this is a great document to take a look at and reference, because we spend some time just exploring the process that we go through about thinking about a rational function. You will find this document on the Graphing Rational Functions PowerSchool Learning page, and it's a slideshow. And the other thing that is the second slide after this one that appears there has some practice problems and a step-by-step approach to graphing simple rational functions. So those are all some reference documents, and I'm going to actually do a practice problem from that slideshow. And I'm going to do that right here in my problem journal. So I'm going to be graphing a rational function. So I'm going to title my problem journal like that. And it is the 14th of November today. Good to put dates and titles so that you can sort of find some good example problems that if you're looking to study up on how you graph rational functions. And the function, I'm going to choose the second function on the second slide to practice with. It's g of x equals 3x plus 1 divided by x minus 2. And just following the steps listed on that slide, I can do each of these pieces. And if I'm not exactly sure how to do it, of course I can reference the slide or the frame, that blue document. The first thing I'm going to do is draw my x and y axes. I'm just sketching this, so I don't need to scale my axes necessarily, but I will label them x and y. And notice that my axes are right along the grid here. And the first thing we do when we're graphing a rational function is we look for the vertical asymptotes. And I have to consider the values of x that cause this function to be undefined. And we look in the denominator, and we see that anytime the denominator is equal to 0, that's going to cause division by 0, which is undefined. So x equal to 2 is a value of x that causes this function to be undefined. So that is where my vertical asymptote is going to be, right at x equal to 2. And I'll draw this dotted line like this. And I'll just label the line with its equation, x equal to 2. Next, I want to consider the end behavior of this function. And the reason I'm doing that is because I want to see if towards the ends of this function, if the graph approaches a certain value. And it does. If you think about plugging a really, really large positive number in for x into this function, like 1 billion, this would be like 3 billion plus 1 on the top, which is really just 3 billion, and 1 billion minus 2 on the bottom, which again is just really 1 billion. So I can ignore all these constant terms and really just think about the end behavior in terms of these two terms on the top and the bottom. And really let 3 billion divided by 1 billion is really just 3. So this graph approaches 3 as x gets bigger and bigger and bigger and bigger. If you think about the other direction, as x becomes more and more and more negative, it's like negative 3 billion divided by negative 1 billion, which is also 3. So I end up with a horizontal asymptote at 3, and I will indicate that with this dotted line. There's my horizontal asymptote, and it's at y equal to 3. So the last thing we have to do is, in our sketch, is just draw the curves. And in order to do this, I'm going to test a particular point. There's, just to imagine, if I plug 0 into this function, I'm either going to get a point somewhere along here, and that would indicate that my curve will be in this space. And if I get a number greater than 3, then I would expect my curve to be up here. And so if I put 0 into this function, on the top I get 1, and the bottom I get negative 2. So 1 divided by negative 2 is negative 1/2. So my graph actually goes through this point right here. So I know that it's going to be down in this space. So I'm just going to draw it now. Might as well use that point that I discovered. Put arrows on the end of my curve to indicate that it goes on in these directions. And you can see that my graph approaches the asymptote, the y equals 3 asymptote, the horizontal asymptote in this direction. And it approaches x equal to 2 when I move down in this direction. So I understand the nature of this equation pretty well. So I know that my other piece is going to be up here. But that's not always the case for more complex rational functions. So instead, let me just think of a number that's on this side of my graph, like x equal to 3. And let me plug that in. When I plug 3 in for x, I get 9 plus 1, that's 10, divided by 3 minus 2, that's 1. So 10 divided by 1 is 10. So when I put x equal to 3 into this function, I get like y equal to 10, something up here. So that indicates that my curve is going to be up in this quadrant. So I'm just going to sketch that in. It's going to kind of move in this direction. It's just a sketch, so if I could do it over again, maybe I would move my axes to a different place. But I'll just extend my asymptote up a little bit. And that's my graph of this function, g of x, right there. That's my sketch. One other thing I wanted to just do in this particular problem is I want to think about the domain and range, and I want to make a note about what the domain and range are. There's a lot of different ways to write domain and range, but I'm just going to write it in words. I'm just going to use words to describe the domain and range. So what are those things anyway? The domain is all the set of all possible input values. That is, for this function, all possible values of x. So I can say for this function, the domain is all real values for x, all real numbers for x, except for x equal to 2. I can't put x equal to 2 in this function. So this is a statement using words that describes the domain of this function. And the range is all the set of all output values for this function. So that is all the y values that I've graphed here. And you notice that there's a y value for all y values are possible except for y equal to 3. So my range is all real y except for y is not equal to 3. And that is a statement that describes the range. So I've graphed this function here, and then I've described the domain and range just using some words, and that is the domain is the set of all possible input values to a function, and the range is the set of all possible output values from the function. And that's it. You can go practice the other 3 problems on the second slide. Um,